Hey there, science fans! Ever look around at all the amazing things humans have built? Skyscrapers, bridges, airplanes? These feats of engineering don't just magically appear, they are the result of careful thought and brilliant design. And a super important part of that design process is making sure things are safe. Safety isn't just a good idea, it's everything. Almost everything engineered around you has a hidden layer of protection. Your chair is probably built to hold much more weight than just you. That elevator you ride? It's designed to carry far more people than its stated capacity. This isn't an accident, it's a deliberate choice made by smart engineers. They build in extra strength, an extra buffer, just in case. This extra capacity is a fundamental principle, ensuring that even if things don't go exactly as planned, the structure or machine can handle it. This concept of built-in extra strength has a name in the world of engineering. We call it the factor of safety, or FOS for short. It's a crucial idea, a cornerstone of responsible design. Think of it like a safety net for a trapeze artist. The factor of safety in engineering works much the same way. So, are you ready to explore this amazing concept? Let's dive into the science of safety. Alright, let's get down to brass tacks. What exactly this factor of safety, this FOS we've been talking about? It sounds important, and believe me it is, but the basic idea is actually quite simple. The factor of safety is essentially a ratio. Yes, a number that tells us how much stronger a system is than it usually needs to be for an expected load. Engineers use this ratio to quantify the level of safety designed into a component or structure. The formula for factor of safety is straightforward. It's generally defined as FOS = ultimate strength, allowable stress. Ultimate strength is the maximum stress a material can withstand before it breaks or permanently deforms. Allowable stress is the maximum stress that a component is designed to actually experience in service. This allowable stress is always kept well below the ultimate strength. Imagine a steel cable with an ultimate strength of 1,000 megapascals and an allowable stress of 200 megapascals. The FOS would be 5. This means the cable is designed to be 5 times stronger than it strictly needs to be for its normal working load. Engineering is all about being smart and safe. Now you might be thinking, if engineers know the loads, why not just design things to handle those loads? Why the extra? The real world is a wonderfully complex and often unpredictable place. We need that extra cushion, that factor of safety, for some very important reasons. One of the biggest reasons is that loads are rarely perfectly predictable or constant. They are often variable and dynamic. Consider that chair again. It's designed for someone to sit on it, sure. But what if someone plops down heavily? Or a child decides to jump on it? Think about a building in a storm. The wind doesn't blow at a nice steady speed, it comes in gusts. Then there's the issue of material imperfections. No material is absolutely perfect, no matter how carefully it's made. Steel might have tiny internal flaws, concrete might have slight variations in its mixture, wood has knots and grain patterns that affect its strength. Furthermore, the manufacturing and construction processes themselves aren't always flawless. Small deviations from the design can occur. The factor of safety helps to account for these real-world imperfections. And let's not forget something called fatigue. Materials can weaken and eventually fail even when subjected to repeated stresses that are well below their ultimate strength. The factor of safety helps ensure that these parts can endure such repeated loading without succumbing to fatigue failure. Section 4. Choosing your shield. Picking the right factor of safety. So, we know we need a factor of safety. But how do engineers decide that safety margin should be? The answer is, it depends. Choosing the right factor of safety is a critical engineering decision, and it's not a one-size-fits-all kind of deal. It's a careful balancing act, a thoughtful process based on a whole bunch of different factors. Engineers use their knowledge, experience, and established codes and standards to make these crucial choices. One of the most important considerations is the application itself, and crucially, the potential consequences of failure. If a critical component in an airplane wing fails, or a cable on a passenger elevator snaps, the consequences there are far, far more severe. Therefore, applications where failure could lead to serious injury, death, or significant economic loss will demand a much higher factor of safety. Another key factor is the material being used and how much confidence engineers have in its properties. Materials like structural steel are very well understood. Their properties are consistent and predictable. However, for more brittle materials like ceramics or glass, which can fail suddenly without much warning, a higher FOS is usually warranted. The more uncertainty about a material, the more cautious engineers will be. Section 5. Engineering in action, FOS in bridges and cranes. Let's bring this concept of factor of safety to life with some real-world examples. Bridges support their own weight, traffic, wind, and even earthquakes. Designers use high factors of safety to prevent disasters. Now let's shift our gaze upwards to a construction site. Cranes lift heavy loads and operate under immense stress. Critical parts like hoisting cables are designed with significant factors of safety. FOS is a vital tool ensuring the safety and reliability of our infrastructure. Section 6. The Goldilocks zone. Not too much, not too little? Why not just make everything super strong? Let's use an FOS of 100 for everything. That sounds foolproof, right? Well, hold on. Engineering is about balance, like Goldilocks, not too hot, not too cold. We want it just right. Over-design has drawbacks. More material means higher costs and heavier products. Imagine an airplane with an enormous FOS. It might struggle to get off the ground. On the flip side, under-design is dangerous. Too low a safety margin risks failure. The challenge is finding the Goldilocks zone, safe, reliable, and efficient.